So now today we're going to pick up where we left off and start talking about vibrational energy levels. So here we have the same electronic energy wells we saw in the last class, our ground state and our excited state, but now we're going to add some more detail. Each electronic energy well contains many vibrational energy levels. So inside of these energy wells, we have more than one vibrational level within it, beginning at n equals 0 and continuing upwards. So this n equals 0 down here is our n equals 0 vibrational level. Here is our n equals 1 vibrational level and our n equals 2 vibrational level within the electronic ground state. Now, if you recall, this is slightly different from the particle in a box model where our ground state is n equals 1. So here for vibrational levels, we can begin at n equals 2. Now, the misalignment of the electronic energy wells due to a change in internuclear distance has an important effect for vibrational transitions. Recall that our excited state up here is further to the right on our internuclear distance because we are presumably populating antibonding orbitals and the bond between the atoms is extending, so it's further on the right. It is also higher in energy because it is now less stable. So, transitions from a given n vibrational state in the electronic ground state will be promoted to a different n vibrational state in the electronic excited state. So here I've drawn a bold arrow beginning at n equals 0, and if it goes straight up to the excited electronic state, it does not end up in the n equals 0 vibrational state in the electronic excited state. Instead, it goes to a higher vibrational level, and that's because the electronic well is further to the right, so it is misaligned. So shown above is the vibrational state n equals 0 in the ground state being promoted to the vibrational state n equals 1 in the excited state. So this model used to describe the vibration of diatomic molecules is to consider two masses connected by a spring. So this model is called the harmonic oscillator, and that's what we use to describe two masses vibrating. And we presume that they are connected by a spring. We will be discussing in depth the quantum mechanical harmonic oscillator, but it will be useful to first cover properties of the classic harmonic oscillator first. So let's look at the classic harmonic oscillator. So we have two masses, m1 and m2, connected by a spring. So on the left here, we have mass 1, and it's connected by a spring to mass 2. From left to right on the x-axis, we have position. And we can define the position of these masses using their position x. So m1 shows up here at x1. Mass 2 shows up here at x2. And right in the middle, we have our center of mass, xcm. So for something like a homodiatomic molecule, meaning the same in two atoms, like hydrogen, the molecule, our center of mass is going to be equidistant between the two masses. So if mass 1 and mass 2 are the same, so for example, if they were both hydrogen, our center of mass would be right in the middle. In another scenario, we could have two different masses. Here we have m1 being small and m2 being rather large. So again, our x-axis is going to be position. The position of mass 1 is defined here as x1. And the position of mass 2 is defined here as x2. So for something like hydrochloric acid, HCl, this model would apply, where we have hydrogen being rather small relative to chlorine, which is a much larger atom, and it has a much greater mass. In this situation, our center of mass is no longer right in the center. It is actually closer to the larger mass. So the center of mass is right here, closer to m2. And that's shown using xcm. and that is cm, capital C, capital M. I wanted to indicate that it is not centimeters, and that's for center of mass. So, getting back to our spring that's connecting these two masses. When at rest, the spring is at an equilibrium length. If x denotes deviation from equilibrium position, a change can take the form of extension and compression. So if we're in an equilibrium position, we can extend our spring and that'll increase the potential energy, or we can compress our spring and that'll also increase the potential energy. Right here would be our equilibrium distance. There is a force that now becomes involved that resists the change from equilibrium. So if we were to extend the spring, it would be higher in energy, and there would be a force trying to draw the masses back together to being at the equilibrium distance. Likewise, if we brought the masses closer together and compressed the spring, we would have a force going outwards trying to draw them apart. Equation 7.2 describes this force, and force is equal to negative k times x, where x is position from equilibrium, and k is our force constant, which depends on the system. Now, here is where the oscillation comes in. If the masses are separated from their equilibrium distance by either compression or extension and then released, oscillation or oscillatory behavior will be observed. So for example, here we have our spring and our mass. Right here is our equilibrium position. EQ for equilibrium. Extensions, drawing the mass down, results in a force of compression trying to draw the mass back towards equilibrium. A compression will result in a force that's trying to draw the mass towards equilibrium. This would be a force of extension, and vice versa. So if we were to plot this compression and extension over time, what we would see would be a wave. So plotting oscillation over time results in a wave. In the oscillatory motion, the center of mass does not move. And that's when we are dealing with two masses on a spring. In this example, we're looking at a mass kind of bouncing on a spring, and that's to show that when you compress, there's a force of extension going this way, and when you extend, there's a force of compression going the opposite direction. So let's take a look at how to define the position of that center of mass. We do that with this equation. The position of the center of mass is equal to mass 1 times its position plus mass 2 times its position divided by the sum of the masses. So let's take a quick look at an example, if we can squeeze that in here, where we have our first mass is 10 grams and its position is at 3 meters. And our second mass is 5 grams and its position is 6 meters. So if we use our equation, in the numerator we have 10 times 3 plus 5 grams times 6 meters, divided by 10 grams plus 5 grams, we end up with, in the numerator, 60 gram meters divided by 15 grams. The grams cancel, and we're left with a position 4 meters. So if on our x-axis we're looking at position, mass number 1 would show up at 3 meters, mass number 2 would show up at 6 meters, and the center of mass would be right here at 4 meters. And that makes sense, because the center of mass would be closer to the larger mass. Now, to simplify things, two masses connected by a spring can be reduced to a single mass, which allows a two-mass situation to be considered as if it were a single mass. Now, this will be really useful for us in the future. This is called a reduced mass. So rather than having two individual masses kind of bouncing on a spring, we're just going to treat the whole system like it were a single mass. and that is called the reduced mass. And that's using the symbol mu. So mu is equal to the product of the two masses divided by the sum of the two masses, and mu is the reduced mass, and each m is an individual mass. The reduced mass is useful in allowing us to simplify vibration to focus on position only. So let's take a look at force. Force is equal to mass times acceleration, which we often see as m times a. Position is indicated by x, so velocity is going to be the change in x over time, which can be shown as the derivative of x with respect to time, d of x over d of t. Now, acceleration is defined as the change in velocity over time, which ends up being our second derivative of x with respect to time. So our second derivative of position with respect to time. Now, let's take a look at force again, this time using mass times acceleration. Force is equal to ma. Now, if we bring in our reduced mass for our mass, we can also see that force is equal to our reduced mass times acceleration. And then if we bring in our new definition of acceleration, being the second derivative of position with respect to time, we can make this substitution and see that force is equal to the reduced mass times the second derivative of position with respect to time. Now, considering a spring, we can write a differential equation to describe the time dependence of the distance between the masses relative to equilibrium. So, now let's bring back in the idea of force being equal to the negative of the spring constant times position. So, if force is equal to negative k times x, and as we just defined, force is equal to the reduced mass times the second derivative of position with respect to time, then we can set these two equal to one another. So negative kx is equal to mu times the second derivative of x with respect to t. And we can add negative kx to both sides, set it equal to 0, and we get this expression here. Now let's take a look at kinetic and potential energy and define these now for our new systems. So our kinetic energy, given a reduced mass, is now going to be equal to 1/2 mu v squared, where mu is our reduced mass and v is our velocity. Potential energy, given the fact that we are now describing forces and position, is going to be equal to 1/2 kx squared, where k is our force constant and x is position.